Good call. There we go.
I think the answer is A, if that helps.
For sure. Yeah, if anything, I bet that because you're all factorial experts, this will be easier now than it would have been if we hadn't done them. Right? You guys are all going to breeze through this. Oh, don't speak too quick, Curdy. There's for sure. I don't think it's this week. I actually think it's next week, but they're gonna be Sigma. They're coming for you.
Are we doing Riemann sums this semester, or we're not doing?
No Riemann sums.
Okay.
Because if we were, yeah, for sure, there'd be some Sigma notation there.
That's what I thought you were alluding to be honest.
Yeah. Dowd, yeah, sure. Just remind me then. Yeah, sums are sums, right? Like you guys can't avoid it. It's not like sums just appear in one place. Like sums show up everywhere. They're super important. Right? Because it turns out sometimes you got to add stuff, right? Like what are we going to do? Sometimes you got to add stuff. Sometimes you got to add a lot of things. The class is split. I don't know what to choose.
Oh, that's upsetting.
All right, I'm gonna call it in 30 seconds or so. We'll see how it go. Oh, it's neck and neck. Oh,
I'm just really upset that
the wrong one is winning.
No, that someone chose A. That's just what really upset me because it was going to be a mistake.
Somebody just had to troll you. That's how it is. All right. All right, class, you said B. The answer is not B. Nope, not B at all. Okay, let's figure out why. So in these sorts of questions, these sort of like higher order derivative questions, your friend is always just do, the first couple of examples of them and see if you can see a pattern, right? So let me just, what's the question again? So we've got f of x, or wait, which question is this? This is question 7. So we've got question 7 here, and we've got f of x is x to the 2022, right? Which is appropriate because that's the year. And let's just differentiate it a couple times, see if we can see a pattern. So the first derivative is 2022 x to the 2021, right? We know that. That's just the power rule. The second derivative is, now I'm not going to actually multiply these together because that's kind of messy. But you just basically do the same thing, right? Where you, again, use the power rule and you bring the exponent down and then subtract 1 from the exponent. And let's maybe just do like one more of these, see if we can see the pattern. 2021, 2020, x to the 2019. Okay, so it seems like every time we take a derivative, we're just basically, we're, or here, maybe let's just kind of say, what do we think the nth one is? Well, it seems to be, we're going to take 2022 and we're just going to keep multiplying it in very factorial like, but not the full factorial, because the full factorial multiplies all the numbers less than 2022, right? And that's not what we're doing. We stop after a while. So in particular, we stop at 2022 minus n plus 1, right? And then we do x to the 2022 minus n, like that. Does everyone see like how I got that formula? Like I suspect some people are bothered by the n plus 1 here, but let me know if you are. Yeah, okay, some people are. Basically what I'm doing is I'm just pattern matching, right? So I'm trying to say, okay, look, when this number up here is a 3, right? Here n is equal to 3. How does this compare to 2022, right? And what's the last number here? Oh, it's 2020. That's not 2022 minus 3. It's 2022 minus 2, right? So it's minus n, but we had to add 1 back more. Same thing over here. This is when n is equal to 2. This isn't 2022 minus 2. It's 1 more than that, right? And this isn't 2022 minus 3. It's 1 more than that. Does that make sense? All right, so I'm just looking at what is that last number? Yeah, it's not quite 2022 minus the number of derivatives. It seems to always be just 1 more than the number of derivatives that I took. Whereas for the exponent, it is actually just 2022 minus the number of derivatives that we did, right? So this is the final answer. Unfortunately, when we look at our options, our multiple choice options, this option doesn't appear. But that's okay, because we've done counting arguments before, and we've seen this sort of thing appear. Namely, it looks like a factorial, but I haven't, I've kind of truncated it, like I haven't done the last terms. So we're going to instead rewrite this as 2022 factorial, right? So I'm kind of doing this in general, not just for the one it says. So I go all the way up until 2022 minus n plus 1. So what did I get rid of? I got rid of everything after that. Like so. Okay, and so this is the formula for the nth derivative. Like the question asked us in particular for the 22nd derivative, and we can sort that out in a second, but this is how you'd actually kind of do it for the arbitrary nth derivative. Shantae, specifically which part is bugging you? Right, okay, how do I get rid of the plus 1? So let's take a look. Let me take this part here and move this down. Okay, so we've got 2022, 2021, ... 2022 minus n plus 1. Okay, so we're all fine with that, right? Now, what did I get rid of? So, let me draw like a little line here. This is where we want it to stop, right? So if I kept going, if it was actually 2022 factorial, what's the next number? Right, like this. Right, because you just keep subtracting 1, right? So what I've effectively done then is then I'm going to take that whole thing and divide it by 2022 minus n, 2022 minus n minus 1, ... 3 times 2 times 1. Right? Because I have to, like, everything that I wrote after the dotted yellow line has to get canceled out because I want the sum to stop right here, right? I want that to be the last term. So everything else after that has to get canceled out. And if you look at, this thing right here, what is that? Well, that's multiplied together all the numbers after that one, right? After the first one. Does that make sense? Like this might be bugging you because there's a lot of n's. Like if we do it for this case where n is actually 20 or 22, right? We would have 2022 times 2021 ... times 2000, right? No, 2001. And then, so I'm going to draw 2000, 1999, ... 3 times 2 times 1. And again, everything that to the left of the yellow line has to survive. So I only want to cancel out what's to the right of the line. Right? And what is that in total? That's 2022 factorial divided by 2000 factorial. So the n plus 1 disappears because I want the n plus 1 to be that like negative n plus 1 term to be the last term. So I'm dividing by all the terms after that. No problem. Shunze, are you okay too? Do you kind of see how that works? Okay, cool. All right, so we can see, right, that the answer should be the one that has this as a coefficient, and that was answer D. Okay. Any other questions about that? Okay, let's here, this one should be quick then. I'm going to jump this one. So this is the same question now, only slightly more abstract. So based off of, oops, I just reshared it. So based off of what we just talked about, what should this answer be?
Can we ideally not choose A either? I'm eliminating one option for you guys.
Maybe. Maybe it is 0.
The derivative of a polynomial. I mean, tends to 0.
Could be 0. Could be 0.
Sure.
Yeah, absolutely could be.
I mean, it has to be 0 after n, right? Theoretically.
Right.
Oh, that's actually a great question. You can argue that, like, depending on what the k value is, the derivative is indeed 0 technically.
Mm-hmm.
What k is less than?
All right. 30 seconds. Curdy, the answer to that is to wander around until you find it. Like, unfortunately, that's legitimately the answer. Like, you can just ask people on campus, but remember, of the people on campus, half of them, statistically, actually probably more than half of them, also have never been to campus before, right?
That's
so
so
you got
true.
to, right? But ask an old person, maybe try and find somebody who looks like they might be a professor. Ask them.
It's kind of crazy that 50% actually have probably never been to a university campus yet.
Yeah.
It's kind of crazy.
Yeah. I mean, like, Davis for me is a pain in the butt because there's like 2 halves of Davis. You know what I mean? Aziz, like there's the part with all the labs and then the part with the classes. And like you're looking for Davis 2072 or whatever. And you can find Davis 2070 and it's a lab, and then 2072 is in a completely different part of the building.
It's the first floor Davis that got me, because the numbers, there's no system there.
Yeah, it's random. They assign numbers at random. It's just the dumbest thing.
Yeah. The newer buildings do a bit of a better job in like number coordination, but the older buildings like Davis specific was not.
And also, so here I'm going to stop this, and I'll show you all the timetable thing in a second. But yeah, okay, so wonderful. So class, good job. Yeah, the answer is D based off of what we just talked about, right? Like the answer is exactly D. Like if you'd put n is equal to 2022, you would have gotten the exact same answer as we did last time, right? And Aziz kind of spoiled it, but without doing this question.
I realized I wasn't paying attention.
So there's another version of this question, and the only difference is here k is bigger than n rather than is less than or equal to. And in this case, the answer would be A, right? So
it's so funny because I kind of flew completely over my head.
Yeah.
I was making a joke out of it first, and I'm like, oh, k is smaller than n. What
yeah. And is everyone okay with why the answer is 0 in this case? Like, because you've differentiated more times than there are powers. Okay, yeah, so I got a question, which is why does it make a difference? And yeah, this is a great question. So here, let's try it out. So let's say I give you f of x is equal to x squared. Okay, well, if I take one derivative, no problem. If I take two derivatives, okay, no problem. And then, eventually, if you differentiate a polynomial too many times, it becomes 0. And the moment it becomes 0, it stays 0 forever, right? Like it'll never become something else because the derivative of 0 is always just 0.
I mean, I feel about that too, if that helps.
Yeah.
I drew like a complete brain fart over there until I was like, oh, now I see what's going on here. That's a great.
Yeah, so the value of k matters, right? Rafid, does that make sense? Do you see why it matters? Okay, cool. Yeah, so everyone, that's kind of why there's this subtlety about like whether k was, right? So here k is bigger than n. This isn't the question you did, everyone, right? Like the answer to this one is A. And then when we come down here and we make k less than or equal to n, then the answer is D, right? So sometimes you have to be a little bit careful about that and just make sure, that you're not, that you're paying attention to how many derivatives you actually take. Okay, here, let's do,
if k is equal to n, won't it just be then just n factorial technically?
Yes, yeah. But that's true like when k is equal to n as well, right? Like this formula is still true, right? Because you divide by 0 factorial, which is 1.
That's true.
What happens in question 9? Why is it not 0? Well, so same thing with x squared. You can see until you take two derivatives, the derivative isn't 0, right? So this exponent here tells you how many derivatives you could take before you ended up being 0. So in question 9, right, the question we did where the correct answer was D, it said if k is less than or equal to n, so you take fewer derivatives than the exponent, then you'll get something which is non-zero. Right? Yeah, okay, perfect. All right. Now, do y'all want something like an easier one, or do you want a harder one next? Like, what are you feeling? Do you want something a little bit trickier? You want a hard one? Are you speaking for the class? Okay, well, I mean, everyone seems to want a harder one. Okay, so we'll skip that one. Oh, what happened? Don't just ignore that. We'll do this. Okay. Oh, this is not responding to me. All right, let's try this one. This one's a little bit trickier.
Mm-hmm.
Oh yeah, and let me pull up that thing to give you all a hand about the, yeah, because it's crazy how many students don't know this exists. Okay, so for some crazy reason, so I put it in the Zoom chat, a bunch of students don't know that this website exists, right? Now, the great thing about this is if you look up your course in it, it will tell you what room you're in. And if you click on the room, it gives you a map to the room. Right? Yeah, exactly. Yeah, I always use the site because I can't see things through Acorn. But if any, so Curdy, if you can't find a room, click the room, right? Like find find a course that is in person and just try it, right? Like choose a random course like Philosophy 101 or something, and it'll have some room like Davis 2072. And if you click on it, it pulls up a room, like a map of Davis, and will show you where 2072 is. Right. And so, yeah, that's helpful. I mean, it requires a little bit that you understand how to like read the map, but the maps aren't too bad. And usually you can get a feel for it. If nothing else, because it does give you the room numbers around it, you'll be like, oh, okay, I can see according to this map that I'm here. And so I need to walk down this hall and I'll be there. So yeah, that hopefully will help you find your rooms.
Also, just show up like 10 minutes earlier. Once you kind of are right the vicinity, you can just kind of wiggle your way around and you'll find it at the end.
Yeah, most rooms aren't too bad. The only really bad ones I think are like the first floor Davis rooms, which are a nightmare.
Horrible.
Yeah, the first floor Davis rooms. KN 137 isn't hard to find, but KNF is like if you go in the wrong door and you end up in the wrong part of the building, it's weird.
You just have to go through the whole rotunda to get.
Yeah. Terrace, thank you for very good. Yeah.
I'll plop that into my compass.
Yeah. MN is pretty easy. I don't think there's anything tricky in MN, right?
Airfield's also.
Yeah, IB is pretty easy. CIT is obvious. CC, I mean, like it's one of the big. It's one of the big ones. Like presumably at some point on campus you'll go and like get your student card. Like that's where CC is.
What is B? I'm not sure what that means.
I assume like IB, Joseph is what you're asking, or
I don't know where the S came from.
Yeah, it's the instructional building.
Was it instructional? Is that what the
I think it's instructional because it's only classrooms. This is an IB, right? There's no offices, no labs, anything like that.
I've been like a part of UTM for like 8 years and I never knew that, to be fair.
Yeah, I think it is. I mean, there's also a campus map, right? Like for those of you, Aziz, can you find the campus map? Maybe I'll let you know.
Yeah, I will.
Right. So Daniel, what you want to do is put your course into that link, right? So if you click on advanced, you can search by a course. You could like plug in MAT133 or Eco 201 or whatever, and it will bring up the timetable for you. And in that timetable, it'll say what classrooms are, like what classes are in which rooms. And you can click the room, like the room is actually a link. And if you click the link to the room, it will take you to the map. There you go.
And that's the map right there.
Yeah. Okay, I'm going to close the polls in 30 seconds. Yeah, campus isn't too confusing. It's a little big though. Yeah, Devin, I am. You should be able to see it in the top of the screen, it should say. Right, like the top left-hand corner. Yeah. Yeah, it's a little big, but you'll be fine. Okay, let's end the poll here. Let's take a look at how we did. All right, this is awesome. Yeah, I mean, the majority of the class said C. C is absolutely the correct answer, so good job. Let's take it up to see why it's C in case you didn't quite get the answer. Wow, my screen is really not, it's really touchy. Oh, and then I pulled up my, okay, you can still hear me, but I can't hear you. I pulled out my headphones. Hold on a second. There we go. Okay, so this is question 11. Right, and it says, you know, find the nth derivative if f of x is just 1 over x. Okay. So again, what we're going to do is we're just going to compute the first, 2 or 3 derivatives and see if we can find a pattern. So f prime of x is negative 1 over x squared. And I really recommend everyone, when you're doing these problems, don't multiply your numbers together. Just because, you often you're looking for patterns, and if you multiply your numbers together, you might not find them. Okay, so the next one is going to be 2 over x cubed, right? Or we could do that as like 2 times, well, let's just do 2. And then f double or triple prime is negative 3 times 2 over x to the 4. Maybe let's do another one. F to the 4 is 4 times 3 times 2 times 1 over x to the 5, like this. Okay, so you just grind a bunch of them out. Don't, like I said, don't kind of like plug any numbers in. If you want, even, you can see that it's alternating signs. Would it be fine if I brought the variable to the top? Oh, and wrote it as like x to the negative 5? Curdy, is that what you're asking? Yeah, that's totally fine. Yeah, absolutely nothing wrong with that. And in fact, you can see here, everyone, like it's alternating signs, right? Like the first derivative is negative, second derivative has a positive sign, third derivative is negative, fourth derivative has a positive sign. So I've actually kind of done the multiplications there, but secretly there's this -1 that keeps appearing everywhere, right? So really this thing here is -1 times -1, 2 times 1 over x cubed. This one is -1 3 times 2 times 1 over x to the 4. And this one is 4 times 3 times 2 times 1. So if I really hadn't, don't do the cancellation. How do you actually calculate this? Okay, sure. Yeah, Gerber tab. So here, let's do one more. Okay, and maybe let me do this one slower. So here's what we have, right? Here's the fourth derivative. So let's differentiate that. So the fifth derivative is the derivative of the fourth derivative, right? Okay, so let me just plug this formula in for the fourth derivative. Let me plug that in. So I get -1 to the 4, 4 times 3 times 2 times 1, all over x to the 4. Okay, now the numerator here is just a constant, and we know that we can just take the constant out, right? Like that, and then differentiate 1 over x to the 4. So we don't really need to worry about this thing, right? It's got to come along for the ride, but it doesn't really affect the derivative. So we're going to have to figure out what that is. Now, when we differentiate 1 over x to the 4, it's probably easiest to, first of all, you could quotient rule this if you really wanted to, but that's actually a lot of work. So what I'm going to do is kind of what Curdy suggested and write this as x to the -4. When I do this now, I can use the power rule and write this as, wait, what am I? Did I put the 2 too soon? X cubed, x, oh, sorry, this should be x to the 5. Why did I write x to the 4 everywhere? Sorry about that. Okay, now I'm going to power rule this. So remember how the power rule, right? I'm going to take that and I'm going to put it down here. And then I'm going to subtract 1 from the exponent. And that gives me -5x to the -6, like that. Okay, so that I'm going to take that now and I'm going to plug that into here. And if I do that, I get -1 to the 4 times 3 times 2 times 1 times -5x to the -6. Okay, and I am going to, take this -1 and just kind of put it in here, because that's just where I'm collecting the minus signs, right? X to the -6, and you could leave it like that if you want, or you could divide by x to the 6. That's the same thing, right? And that's how we do that computation. Does that make sense? So it's the power rule, but kind of written in a strange way because we're doing 1 over, but it's still the power rule, right? The power rule actually works for any real number. I mean, that's a lot, but yeah, we'll see. Okay. Is everyone all right with this computation? It's okay. Yeah, exactly. Yeah, for all those derivatives is what I did. And so now if we come up here, what we need to do is we need to figure out the pattern, right? So I'm going to say now, let's suppose I take n derivatives, right? And so in this case, n is equal to 3. In this case, n is equal to 4. In this case, n is equal to 2. And what we're doing is we're looking for patterns, right? So what I see is when n is, when n is 4, I see 4 factorial, right? When n is 3, I seem to see like 3 factorial, and I see 2 factorial, and I see 1 factorial, right? So this number to me looks like n factorial. So I'm going to write that down. The exponent, right? If I look at the exponent here, it always seems to be just 1 more than the number of derivatives that I've taken, right? It always looks like it's n plus 1, so that's a good sign. And then the last thing is that it's alternating signs, but I've kind of accounted for that here, right? And so that's what we get. All right, everyone, and that was exactly C. How come that exponent is not n plus 1? It is n plus 1. I'm not certain what you mean. In the numerator, I mean, that number, well, because it just doesn't match up, right? Like think about what -1 squared is. That's just +1. And this number here is +1, right? What's -1 cubed? That's -1. Oh, this number here is -1. Right? And really, the power of the -1 there isn't important. The only thing that matters is its parity, namely whether it's even or odd. If I change this to -1 to n plus 2, still the same answer, right? Because the -1 to the power of n and -1 to the n plus 2 are exactly the same for all n, right? They're both, just plus or minus 1 at exactly the same time. So I could have changed it to n plus 2. I could have made it like n plus 18. As long as it's n plus some odd number or minus some odd number, it's going to give me the same number every single time. So the only thing we're really looking for here is parity, right? We want to know, is it positive when it's even or is it negative when it's even? That sort of thing. All right. All right. So do you want a slightly even harder one? I mean, I only have so many left, so I'm going to say yes. Any other questions about this one? Everyone's okay though? All right, I'm going to assume everyone's okay. Do, 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 do. Connie, we could. That one's actually not too bad though. Like you could do it now if you want. I can just check your answer. But yeah, I hadn't planned on doing that one. Like the nth derivative of it. Okay, okay. So I want you to start computing derivatives for me and tell me what you get. No. Okay, 30 seconds on this. Okay, a couple seconds. And go. All right, so we're pretty confused, right? The class answered B as kind of like the plurality. We'll see. Maybe it's B, maybe it's not. Let's see if we can figure it out. But like, there's a good number of people in sort of all 5 of these things, right? Well, not always. It can lead to some nasty stuff. Like e to the x, you're right, Namir. Like e to the x is generally very nice to differentiate. Rafid, yes. But it depending on what else you throw in there, kind of like the nasty part for this one is that x, right? That x in front of it makes it a mess because now we have to product rule. But you're right. Like normally, most of the time, e to the x is pretty nice. So, all right, again, let's just try differentiating. So what's our function? It's x e to the x. So let's differentiate the first time. When I do this, I have to use the product rule. So derivative of the first times the second plus the derivative of the second times the first, right? Everyone got the same thing, hopefully? Good. Now, you are free to expand, like you can either factor this if you want or leave it the way it is. It doesn't matter. In some sense, though, actually factoring it might make our lives a little bit harder. And let me show you why. So let me just kind of leave it for a second. And let's now compute the second derivative. Okay. So the derivative of e to the x is just e to the x, right? It's its own derivative. And now you get to this part and you're like, I don't think this was easier, man. Like you know, now we have to differentiate that using a power rule or a product rule. And I say, well, no, actually we don't. We've already differentiated this, right? All right, we already differentiated it. So I'm just going to take this answer and throw it in here, like that. Do you see that? Of course, if you wanted to, 100%, you could factor it and do this again, like that. Yeah, right? And then, so now when I do the third derivative here, those first two terms are just e to the x. So of course, I could put them together, but I'm just gonna kind of like leave them out here for our purposes. And then I'm gonna differentiate that. Well, again, I've already differentiated that, e to the x plus x e to the x, right? And then when I do the fourth derivative, okay, this isn't a trick. I'm not doing a trick here. You could do this however you like, and you'll still get the right answer. You don't have to do it this way. Why isn't it xe? Okay, sure. Let me answer that one in a second, because that is a fairly common mistake, and we should address it. But let me just do this one. And then again, we differentiate that, e to the x plus x e to the x, right? So it seems like every time I differentiate it, I just keep picking up this extra e to the x, right? So now if I collapsed this, I would get 2 e to the x plus x e to the x, 3 e to the x plus x e to the x, 4 e to the x plus x e to the x. Or if you factored out the e to the x, right? And so at the end of the day, and that is A. Okay, now I got a very important question, which was the following. So question. So why isn't the derivative of e to the x equal to x e to the x minus 1, right? Like applying the power rule here, right? So I just want to be clear because this is written down, right? This is not correct. So I don't want you to see that and accidentally think that it's correct. The important distinguishment here is the difference between writing something like the derivative of x to the power 5. Notice it's the variable is the base and the number is the exponent, right? So when we have a function like this, we can use the power rule. Okay, but when we differentiate something like e to the x, here the number is the base and the variable is in the exponent. Okay, so if the variable is in the exponent, we have to do this differently, right? In general, the derivative of a to the x is a to the x ln a, and the derivative of x to the power of a is ax to the a minus 1. Okay, so it really is going to make a difference as to where the x is. Okay, so lots of students do this by accident. Okay, don't do this because this is a really bad place to lose marks. Okay, does that make sense? Do people see when you're supposed to use the power rule and when you're like why you can't use the power rule in these situations? You can't use the power rule when the variable is in the base. No, that's the opposite. You can't use the power rule when the variable is in the exponent. Right? This is the power rule. And in that case, yeah. So in that case, the exponent or the variable is in the base, and you can't use the power rule when the variable is in the exponent. And as long as you keep that in mind, you'll be fine. Yeah, no problem. Okay, we're running a little low on time here. Should I just cut the class and then we can go into office hours, or do you want to do one more kind of like really tricky one? One more? All right, people are feeling good. Hopefully you look at that, you're just like, what? Yeah, but I know you want office hours. We'll be there soon. We'll be there soon. Maybe for this one, I'll just say, I'll tell you what the right answer is. So we'll give everyone a chance to try and work through it. I'll tell everyone what the right answer is and how you would check that your answer is correct. This is a thing, though. This is a thing that occurs in real life. This isn't just, we didn't make this up. This is legitimately a real differential equation. All right, see you, Brandon. You too. Have a good weekend. Good luck. Yeah. See ya, Conch. Good, good, Sam. How are you? Good, good to hear. Connie, no. Man, this is really tripping some people up, eh? Sure, yeah. All right. So for the sake of brevity, I'm going to give you 30 seconds, and then I'll tell you what the right answer is and how to do it, but I won't do it myself. Sure. And the reality is that it doesn't matter. So I'm like, you're going to have to do conjugates for that one anyway. Yeah, no, Rafid, nope, it's not that one. This is a great question. I love this. And again, we didn't make this up. This differential equation is a real life differential equation. This one is real life. So the class is pretty split, right? In fact, the one that has the least number of votes is the correct answer. The correct answer is X. Okay. So what you're going to do to check each of your answers is I want you to actually plug the function P into this equation, right? And if you plug here, maybe I'll just annotate here really quickly. So for example, if we plugged P of X equals 1 into this equation, well, what is the derivative of P of X equals 1? It's 0, right? So this whole thing becomes 0. And what we're left with is 2 times 1 is equal to 0. Is that equation true? No, right? So it can't be A. Okay. Now what you're going to do next is you're going to take P of X. You're going to plug it into there. What's the derivative of P with respect to X? It's just 1. Okay. So now this equation becomes d dx 1 minus 2, or sorry, 1 minus, how easy is it to erase here? Not very. 1 minus x squared plus 2 times P of X, right? What is that? Negative 2x plus 2x. Voila, that equals 0. Right? Yeah. These two are not solutions either, and you can check by actually plugging them in. It turns out, you might ask, where do these come in? If you change some of the numbers, like if you change this 2 here and this 2 here, if you change these numbers to 3, I'm pretty sure that C is correct. And we change them to 4, I'm pretty sure D is correct. Okay, yeah, dp dx. Yeah. So dp dx is just the derivative of whichever of these functions you're playing with, right? Yeah, so B, the derivative of P of X is 1. Yeah, so this is what's called a differential equation, everyone. And the reason why we teach you calculus, a lot of you might be like, well, calculus is stupid. Like, why do we learn it? And for the most part, I would agree. But the reality is that the majority of real life things it's not about differentiating. What you do is you often have rules which govern your system, whether your system is a market or options pricing, or is the weather, or is gravity, or whatever the case might be. You have a series of rules. And when you translate those rules into calculus, you'll often come up with something that looks like this. And then what you do is you try and solve this thing for P. Now, obviously, in this case, this is actually really hard to solve. So we gave you the solutions and said, just check. But in real life, you can find these things. And then once you have these equations, you try and solve them, right? And in fact, this is part of the reason why it's so hard to predict weather, is because it turns out that the differential equations which you would solve in order to get weather are highly conditional upon your what are called your initial conditions, like the current temperature and pressure and so on and so forth. And so small changes in those things very quickly lead to dramatically different long-term behavior. This is called the butterfly effect. Some of you may have heard about it. But yeah, so this is the sort of thing that you would study in a differential equations course. It's not the sort of thing we'll study here. We used to back in the day, but we've since cut it. But that's that sort of idea. So yeah, d dx here, for example, means differentiate everything that comes after it, right? What was essentially 1 minus 3x? What do you mean by that, Curdy? What was 1 minus 3x? The first line, not quite certain. I don't see any 3. Oh, yeah. So it is 1 minus x squared, right? So that's why it became negative 2x. Yeah. I don't know what your comment is about 3x though. I'm a little confused about the 3. Okay, cool. Okay, sweet. So hopefully that kind of takes care of that. Let me unannotate. Then we'll go into office hours here because I know lots of people have lots of questions. Okay, everyone's good? Otherwise, we'll start office hours. Aziz, I assume you're taking off?
I'm answering a few private, like direct messages, that I'm heading out.
Okay, sounds good. So I've been requested 427 a lot. So why don't we do this? This is a great question too. I really like 427. In fact, 4-27 was a term test question. It was either last year or the year before. I don't remember exactly what year it was, but it was a term test question. So this is a great question to ask. So without sort of copying it, everyone, you can pull up your copy of the book and find it, right? It's on page 132. So you roll a d6 and you record the number as x. So x equals roll a 6-sided die. And then depending on what x is, you flip a coin that many times and you record the number of heads, right? So this is the number of heads in x dice flips. Okay.
I did this question yesterday in my office hours as well, by the way.
Nice. Yeah, I love this question. It's such a good question. This is 100% a TJ question. TJ came up with this. And when he showed it to me, I was just like, oh man, that's a great question, TJ. Okay. So question A is compute y equals 4 given x equals 6. Now, this isn't really a conditional probability question. It kind of looks like it, but it's not. Because if we translate what this is asking to English, what does it say? What are we trying to determine? Anyone? Not expected value, not yet. Yeah, so exactly. So we're trying to determine the probability that y equals 4 given x equals 6. But if we translate what y and x mean, this is the probability that we get what if we do what? Did you get 4 heads given it? Yes, Christian, but the 6, how many heads given are 4 given that 6 is rolled, right? So what does a 6 being rolled mean? When you flip a coin, Owen, exactly. So Owen sent me a direct message. Owen, I hope you don't mind that I dox you here, which is that when you flip a coin 6 times, what's the probability of 4 heads? Right? And Ahmed, yeah, exactly. And Ariana as well, right? 4 heads when you flip 6 times, right? So this is the probability of 4 H's in 6 coin flips. Okay. So we could have asked you this before doing CSEs. We could have done this before even doing conditional probability, right? So before we did conditional probability, if we said you flip a coin 6 times, what's the probability that you get 4 heads? What is your answer? You would raise your hands. Right? Isn't that how it always used to be? That's true. That is, and like one of the things I've said, Connie, is that one of the pros, as far as I'm concerned, from teaching online is that students do actually tend to, oh yeah, it's okay though. I mean, you know, pride is totally a thing and people are worried about that, but like, yeah, I get it. But people definitely engage more in online, and that's actually a really cool thing. I do enjoy that about the online portion. Oh, and you keep direct messaging me and you keep being right every single time, right? If X is rolling a D6, then why are we writing? So Shanze, I don't know if you're just going off what I've written here, but if you go back and you look at the question, what it says is whatever X rolls, like whatever you roll on your dice, that's how many times you're going to flip the coin, right? So if I roll a 4 on my dice, then I'm going to flip the coin 4 times. If I roll a 6, then I'm going to, yeah. So if I roll a 6, then I'm going to flip the coin 6 times. So that's why a roll of a 6 and flipping the coin 6 times are the same thing. Does that make sense? Yeah, I'd recommend just pulling up the question so you can see it, because I don't want to rewrite out the whole thing. But like, if you pull up the question in the like PDF version of the notes, you'll be able to see it, and then hopefully it'll make a little bit more sense. So Owen, I'm going to dox Owen again, but like Owen sends me exactly the correct answer, and it's 6 choose 4 divided by 2 to the 6. Yeah, Doug, sure. Does everyone agree? Okay, so hopefully we, okay, so which part? Are you comfortable with the 2 to the power of 6? Okay, yeah, you're good with it. Same, are you comfortable with 2 to the 6? So Curdy, what is the sample space? What is the total number of ways, like the total sample space size in 6 coin flips, right? Well, for the first coin flip, it's either heads or tails, right? So there's 2 ways of doing that. The second one, heads or tails. Third one, heads or tails. Heads or tails, right? So there's 2 ways times 2 ways times 2 times 2 times 2 times 2 equals 2 to the 6. Right? Yeah, exactly. It's like great way explanation, because there are 2 results per flip, and it was 6 times. Exactly. Ahmed. Perfect. Okay, so everyone's good with that. So it's the 6 choose 4 that I think is bugging people, right? And this goes back to kind of like our classic probability question, which is again 1, 2, 3, 4, 5, 6. So here are the coin flips, right? Now, what I want to do is count all the number of ways that 4 of these could be a heads, right? Now, does it matter if I put a heads, like I'm trying to figure out the places that I can put heads. So what I'm going to do is I'm going to number those something like 1. So if I put heads here, heads here, heads here, and heads here, I'm going to say that's 1, 3, 4, and 5, right? Arslan, that's a great question. Let me sort this one out first, but then I'll answer yours in a second. And hopefully you all agree that order doesn't matter here, right? So if 1, 3, 4, and 5, and what I'm doing is I'm saying this is where the heads are going to go, right? So that the other ones have to be tails. Order doesn't matter, because if I did it 1, 2, 5, 6, and it still wouldn't matter. I mean, that would be a different configuration though, same, right? Like 1, 2, 5, 6 would be heads, heads, tails, tails, heads, heads. And that's a different configuration, right? So it is 1, but it's a different one. So what we're trying to do is trying to count all the number of ways we can pick, like that we can take 4 numbers from a grouping of 6 numbers where order doesn't matter, right? And that's why we get 6 choose 4. It's the number of ways of choosing 4 numbers from a group of 6 where order does not matter. Does that make sense, everyone? Right, yeah. Or because there's 6 flips, Avi. There's 6 flips, and each flip has 2 possible outcomes, right? A different configuration wouldn't matter still. Like in the sense that yes. So so in your example, Simon, when you said 1, 2, 5, 6, right? If I said put the heads there, 2, 5, 1, 6 is the same configuration of heads, right? I said the second flip is ahead, the fifth flip is ahead, the first flip is ahead, and the sixth flip is ahead. That's the same as the one you originally gave me, right? Those are the same, the heads are in the same flip. Curdy, yes, if order mattered, it would be 6 pick 4, but in this case, right, it doesn't. So that's why we use C. Okay. All right, everyone. So that is A, right? And we're done. But if order doesn't matter, is there a difference? Yes. I mean, those just have different numbers in them, right? So those are different even if order does matter. Right? Because yeah, think about it. So Simon, let's do your 2 examples. Or did you just copy what I did? 1, 3, 4, 5. Yeah. Sorry. So yeah, here is 1, 3, 4, 5. Here is 1, 2, 5, 6. And these are different, right? They have a different arrangements of heads and tails. Yeah, cool. Okay, so B in this question is to compute the probability that y equals 4. Okay, i.e. we want to determine the probability that we flipped 4 heads. Well, Connie, I don't know what you mean quite yet. There is a 1/6 that's coming, but we're not quite there yet. So how could I flip 4 heads? Somebody tell me. Like what are the scenarios that could happen? Oh, and see, Steve, you keep not wanting to say it out loud, but you're 100% correct. Awesome. There you go. And Devin, exactly, right? What happens when you roll a 4, a 5, or a 6? Because hopefully we'll all agree, if I only flip the coin twice, there's no way I can get 4 heads, right? That's not possible. And if I flip the coin 3 times, I can't get 4 heads. So in theory, what we could do is we could write this out. Maybe I'll write it out like this, but we'll say, yeah, most of these don't matter. So it's the probability that y equals 4 given x equals 1 times the probability that x equals 1, right? Plus the probability that y equals 4. This is how we would do it, like from the law of total probability. X equals 3 times the probability that x equals 3 plus the probability, oh, sorry, this should be 4. Y equals 4 given x equals 4 times the probability that x equals 4. Just 2 more. Y equals 4 given x equals 5 times the probability that x equals 5 plus the probability that y equals 4 given x equals 6 times the probability that x equals 6. Okay, so this is called the law of total probability. And if you're not certain about where this comes up, right, so this is the law of total probability. Now, these ones are all 0. Oh, no, that one's not 0. Okay, so these first 3 are 0, right, everyone? Yeah, exactly, Arslan. Yeah. Oh, and sorry, Arslan, I forgot to answer your question as well. Okay, again, let me finish this one because I'm on a roll here, but maybe remind me once I finish this one, okay? Or maybe I can just answer your question for you. What did you say? So the probability that you get 6 heads in 6 rolls, and you said it's 1/2 to the 6? Yes, that would be correct. Yeah. So if you don't care about seeing the answer, I can confirm to you that your answer is right. Yeah. Okay, so everyone agrees these probabilities are 0? Okay, right? So, we're not worried about them. And all we need to do now is figure out these other things. So let's look at this one. So the probability that y equals 4 given x equals 4, right? What's this part right here? What is that probability? So you flip 4 coins. What's the probability that you get 4 heads? Yeah, Connie, exactly. So it's 1 over 2 to the 4. That's the, just like Connie kind of got ahead of me times the 1/6, right? But if you flip 4 coins, there's only one way. And Agam, I think that's probably what you're saying, right? Like there's only one way to get all 4 heads, right? And there are 2 to the 4 possible total options. So that's 1 over 2 to the 4. 4 choose 4 is totally fine. That's also 1, right? So yeah, 4 choose 4 if you want, you could do it like that. And then we multiply by the probability that x equals 4, and that's 1 over 6. Okay, so let me know if anyone has any questions about that portion. Hopefully everyone's okay. And if you are, you can start, thinking about the next section. You don't need to wait for me. Okay. What about this? Now, this says probability that x can be 4. Yes, exactly. Yeah. The probability that x is 4 is if you roll the coin or if you roll the die, what's the probability that it comes up 4? It's 1 in 6 because the die is fair, right? Right. Okay. So second one now, right? So we're done those. So now we're on this one. So this says, what's the probability that you get 4 heads in 5 coin flips? Well, 5 choose 4, but yeah, right? 5. So 5 choose 4 divided by 2 to the 5. Okay, great. Yeah, and exactly 5 choose 4 is 5, Ahmed. And same sort of probability, right? The probability that x is equal to 5 is still 1/6. All right, I like it. People are doing great. And let's do the final one. Well, we actually already did this one, right? And so you add all those up, and that's the probability there, whatever number that is, right? I guess we need it for the next part. So that's going to be 1/6, 1/16 plus 5, plus 5 over 32 plus, what's 6 choose 4, 15? Right? And somebody worked that out for me. So 4 is 14, so 29/64, I think. Right, 36 or 29 over 384. Yeah, exactly. Ahmed and Jack both have your back here. Right? Right, same. So if you roll a die, right? So the probability of x equals 4 is saying if you roll a die, what's the probability it comes up 4? Well, the die has 6 sides on it, right? It's got 6 faces and they're all the same. So that's why it's 1/6. Yeah. So this would actually be a really interesting question because one thing, if any of you want to practice, I mean, obviously we're getting a little late into the night to practice, but if you wanted to practice, you could now try this problem again with an unfair die, right? That's actually a really interesting question. Probably too hard for a test, but if you wanted to try it, that'd be a good thing. So I think it's 29/384, something like that. Hopefully someone can throw that into a calculator and just double check it for me, but I think that works out to be the answer more or less. And then in part C, so C now says, compute the probability that x equals 6 given y equals 4. And you'll notice that this is the opposite of part A, right? Part A was the probability that y equals 4 given x equals 6. In this case, we've switched them around. Now, if that itself, if for some reason I completely didn't understand that I had to, yeah, that would be rough too, right? Like that could totally happen, is that you could accidentally screw that part up and just get hit. But like there's, just a mark or two off, and hopefully it wouldn't propagate too much throughout the rest of the question. So first thing, we flipped exactly. As Agam points out, it's kind of like the thing that this screams to you is Bayes' theorem, right? Because we flipped these around, and that screams Bayes' theorem to you. Now, if that didn't scream Bayes' theorem to you, the other thing to realize is this is the really weird question, right? It's saying, what's the probability that I flipped 6 die, or that I flipped 6 coins, given that 4 of them were heads, right? Doesn't that seem like a weird sort of question? When you get that sort of weird conditional probability, again, that's going to scream to you Bayes' theorem, okay? Can you use Bayes' theorem? I would say it, at least in a word, Connie. Like if you're going to use Bayes' theorem, you should say by Bayes' theorem, and just those 3 words, by Bayes' theorem, and then write out your formula, right? It just really is important there because you signal to the marker what you're doing, and it really, really makes a big difference in terms of the understandability of your solution, right? So just include those 3 words if nothing else. The probability that the dice was what we used to get in our foreheads. Yeah, so it says like, so Davin, the reason why this is weird is because you know that you got 4 heads, but you don't know how many times you rolled the dice, right? And that's why we're saying like, that's the weird version of this question, right? So the weird version of the question is usually a Bayes' theorem sort of thing. Yeah, the probability that we rolled a 6 given there are 4 heads, that's weird, right? So again, this is the Bayes' theorem thing. And in real life, usually the way this gets worked out is like, I think I give an example in the text of medical things. So what you do is you test that whether people are, for example, let's say, you're doing COVID tests or something, and you do it in a lab where if a person is COVID positive or COVID negative, and you give them the test and you see like how many false positives you get, how many false negatives you get, things like this. And then in the real world, well, you don't actually know if you have COVID, right? So you take your test, it comes up positive, and the test manufacturer will say, oh, if you get a positive test, there's this % chance that it's a false positive, that you don't actually have COVID, right? So these sorts of things, yeah, exactly. Yeah, the schema question. So this is what I'm saying. Like you guys might say, well, this is a stupid question. Who would ever ask the probability that x equals 6 given y equals 4? And no, like that's actually important in real life, right? Where you flip a lab around and you go from doing something in a controlled setting to not doing something in a controlled setting. Bayes' theorem really comes up useful there, okay? So what does Bayes' theorem say? So Bayes' theorem says, okay, somebody double check me if I'm wrong here. So it's going to be the probability that y equals 4 given x equals 6 times the probability that x equals 6 divided by the probability that y equals 4, right? I'm pretty sure that's Bayes' theorem. See you, Daniel. Right, so I got Bayes' theorem correct. Hopefully nobody's, that's fine. And we've already computed all the things here, right? Like you'll notice we scaffolded this question, right? We wanted to get you here. So we computed the probability that y equals 4 given x equals 6. So we said that's 6 choose 4 divided by 2 to the 6 times the probability that x equals 6 divided by this thing, which I'm hoping is correct. And if we do that, what do we get? 15/29ths? Right, I'm hoping that's what that works out to be. But like that's, I might have added my fractions wrong, so you can double check that. But that's not as important as understanding like, what I've done here, because you can all check this on your calculator. Is everyone okay with what's going on there and how we would do this? Okay, sweet. So that's how we do that question. It's it's a little bit of a long question, but it really, it's a very nice question. It tests some basic counting stuff, tests the law of total probability, tests Bayes' theorem. It's a beautiful, beautiful question. It's really, really nice. Maybe it is, maybe it isn't. Theodora, sure, there are a bunch of in the queue before you, but I'll put this one in the queue as well. And okay, so Ahmed, let me star yours. like Dowd asked a question too, and I want to make sure I get to that one. So Dowd, can you like point to a question that you were thinking of? Like when you said a continuity limit question, can you just to give me an example? Even I can probably make one up, but I just need to know like specifically what you're looking for. Okay, sure. Do you mean like when you say continuity limit, like checking if a function is continuous or using that it's continuous to push a limit inside? Oh, checking continuity. Okay. Sure. Let me see. So, yeah. Okay. So let's suppose f is the following function. All right, hold on. I'm just going to write it down. And because if you see me write it down, it's going to give it away, right? So like, let me just kind of write it down on a piece of paper really quick here. Plus x, right? So x squared. Is f continuous at 3? If not, classify the discontinuity. So is this the sort of question you want? Like, does this looks fine? Okay, cool. All right, so we got this function here, and you can imagine, like, when you look at this function, x equals 3 is a bad point, right? Like, maybe it's not bad, maybe it is bad. We're not certain, but whatever, that's probably the only point that we really have to worry about. So we want to determine if the function is continuous. Always a great place to start is just remind yourself, what is the definition of continuous, right? So f is continuous at 3 if the limit as x approaches 3, f of x is equal to f of 3, right? That's the definition of continuity. Now, what is f of 3? According to the problem, 7, right? It's this thing, right? The function says when x is equal to 3, that it's 7. Oh, sorry, yeah, positive 3. Yeah, thank you. Thank you, Ariana. Okay, so everyone's good that f of 3 is equal to 7. So what we want to check, right, we want to compute this limit. And if the limit exists, great. And if it's equal to 7, then we're continuous. And if it's not equal to 7, well, then we're not continuous. So now we need to compute this. So now we compute the limit. Okay, so we're going to do the limit as x approaches 3, x squared plus x minus 12 divided by x minus 3. This we can't find the limit as x approaches. Yeah, and sorry, and plus 3, right? Because I accidentally screwed up that first time. I do want everything to be at plus 3, but exactly, we're going to take that top function. Oh yeah, and you corrected it. So we're going to take the limit as x approaches 3 of the top function from either side. Now, it turns out in this case, we're actually lucky and we don't actually have to do the one-sided limits. But of course, if you want to do the one-sided limits, you can. There's nothing wrong with that. But in this case, we can actually do both limits simultaneously. If we try and plug 3 into this, we actually get 0 divided by 0, right? Which is our big sign that we have to do something a little bit more. Exactly. So let's try factoring it. So we'll get x plus 4. And I, of course, know the factorization because that's how I made the question. We cancel out our x minus 3s. Oh, I actually did not mean for this function to be continuous. But hilariously, I accidentally chose it so that it was. But anyway, there you go. Right, so we got our limit. Our limit is f of 3. So it is, the function is continuous. So Dad, does that help? Like help you see how you would check if it wasn't okay. So if Simon, this is a good question. If it's 0/0 and the top is and you know both are polynomials, then it has to be factorable, right? This is one of those properties of mathematics. If a is a root of a polynomial, then x minus a is a factor of that polynomial. That's just always true. Now, I could give you things that aren't polynomials, and then it wouldn't be factorable, and we'd be in trouble. But in the case of polynomials, you can be guaranteed that if it's 0/0, it's always factorable. Right, or it would be continuous. Like what? Let's say I change this to be a +3 in the bottom, right? So now when you look at the top function and you plug 3 into it, it's not 0/0, right? It's 0/6. In that case, this function is not continuous, right? Even though, like, you know, maybe I made things unfactorable or something. Like I could change it so it'd be unfactorable, but maybe in that case you don't actually care because it's continuous anyway. Like you don't get a 0/0, right? What if the bottom part was 7x plus 2? Then would the limit have to be 23 for it to be continuous? Yes. Now we probably wouldn't do 7x plus 2 here at a single point, but maybe it would be a more interesting question if this was like now x less than or equal 3 and greater than or equal to 3, then yeah, we would do something like that, right? Yeah, Shana, you exactly. This function is actually continuous, so it doesn't have a removable discontinuity. If I had originally put anything other than 7 here, you would be correct then, and it would have been removable because the limit existed but wasn't equal to f of 3. Does that make sense? Right, okay, yeah. And so everyone, remember the key thing about continuity is the definition, right? The definition is this thing right here. That the limit is equal to the value of the function at the point. If those two things, you compute those two things separately. If they're equal, you're continuous. If they're not equal, you're not continuous. And then you can classify the discontinuity from there. No, it would still, so I got a question saying, wouldn't it be a jump discontinuity if say the 7 was an 8? And no, because here, let me fix the question so that I don't confuse anyone. Equals, not equals 3, equals 3, and let's say this was an 8. Okay, so the definition of a jump discontinuity, right? Oh, okay, yeah, you're fine. Yeah, oh yeah, maybe if you were doing a less than or equal to, maybe. And because, yeah, in that case, you'd sort of have like a jump discontinuity, but in this version of the problem, it would be removable because the two-sided limit does exist, but, you know, it's just not equal to the function. Yeah, in this case, it is removable. Yeah, but remember what I had before here is like when we were messing around with the question, I had put this here. And with the blue things, it was a jump discontinuity, right? But once you change it back to like equals and not equals, it's removable. Yeah. Yes, so I got a direct message saying, is it an essential discontinuity if it does not exist, i.e. goes to infinity? Yes, absolutely. Yeah, if one of the limits doesn't exist for any reason, okay, it doesn't just have to go to infinity. There are actually other ways that a function like a limit could fail to exist. But yeah, exactly. If one of the one-sided limits goes to infinity or does not exist for any reason, then yeah, it's an essential discontinuity. Now for us, mostly that will be shoots off to infinity, but it is possible to have other types of failures as well. Yeah. Okay, I got, oh yeah. Oh man, okay, there's so many things here. So A7 Q2 part 2 and then 4-32. Okay, so there's a couple of things here. So I got a request for 434. If I recall correctly, there might actually be an issue with 4-34. Let me just read it quickly. There was a bank robbery downtown. The witness can you stay? Yeah, I think actually 434, whoever asked for it, doesn't have enough information to be done. So I think actually 434 is not a good question. So you can kind of skip it. Because yeah, I think originally I made an assumption when I made this question because it was way back in the day. And I think 434 actually isn't solvable in its current form. So it does need a little bit more. Oh, this is interesting. Connie, usually it's the other way around. We'd be more suspicious if you did like really well on the final, but don't worry about it. I would never give anyone an academic offense because they did better or worse. Some students just do really well on finals. Some students do really poorly. And I will never give an academic offense on like, just because you had a bad day or or studied really hard. Like, I don't think that's fair, right? I mean, there's nothing I love more as a teacher than seeing a student work really hard and do really well on a final. That by itself would not make me suspect an academic offense. No, we look at, in fact, everyone, this is kind of important for everyone. When we do academic offense stuff, at no point do we ever look at anyone's name, previous marks, or previous academic offenses, right? The way CrowdMark works is we can't see any of that information. Right? Okay. So when we do academic offenses, I don't see your name. We don't see your name. We don't see if you have any prior academic offenses. We don't see your grades. And that way, the only way that we can do academic offense stuff is based off of that assessment itself, whether it's a test or whether an assignment. And that way we can't be bringing in our personal prejudices or biases at all. And it's not until the very end that we match the books with the names and, so that emails and everything can be sent out. But at no point in that process does anyone see what your name is or any of your prior history. And that's to be fair to you, right? So that always academic offenses are done only on the basis of the material itself, which I think is the right way to do it, right? That's the fair way of doing it. Okay, so Ahmed, I think you asked for a lot. So I just want to make sure everyone gets a chance here. I am going to try and hit 423 here. So I was asked about A7 question 2 part 2. Let me just pull that up really quickly because I feel like that's probably an easy one I can answer really quickly. So because I was just asked like, why did I add instead of multiply? Why did you add the probabilities of each shape and multiply their number? Sure, let me just pull it up here so I can see. So Connie, like I said, I wouldn't worry about it. Like if you, if you're honest, I don't think they're usually an issue. And the more you write, the less your paper looks like it would be suspicious as well. So don't hesitate to write more. Yeah. So you could definitely, it'll be open book. So you can do anything you like, recordings are like notes, right? So you can reference recordings and notes as well. Okay, repeat the experiment in part 1, but now suppose that each number describes the probability that you choose the shape out of 25. For example, the triangle with 4/25. Okay, yeah. So person who asked me for this question, when we compute the expected value, what we're doing is we're multiplying the number of sides, right? So when we compute the expected value, let's not use blue for this. So when I compute the expected value, what we're doing is we're going to multiply the number of sides times the probability of getting those, like that number of sides. Okay? And then we're going to add them all up. So in the case of the triangle, so everyone, this is A7, maybe let me write this down. This is assignment 7, question 2, part 2. So the triangle, the first triangle has a 7 in it. So the number of sides is 3. The probability that we choose that triangle is 7 out of 25, right? The next triangle has a 4. So it has 3 sides times the probability that we get that triangle is 4 out of 25. Then we've got a square. Square has 4 sides. Probability of getting it, 5 out of 25. Next square, 4 sides. Probability 0 out of 25. And so on and so forth, right? And that's just where all these numbers come from. But the solution did, yeah, sure. That's because this is 3 times 11 over 25. Yeah, the probabilities are given in the shape. So what the solutions do are say, okay, well, what's the total ways that I could get a triangle? Oh, there's 7 ways of the first one and 4 ways of the second one. So combined, they're 11 out of 25. Does that make sense? Yeah, sure. Factor a 3 out of this, right? So 3, 7 25ths plus 4 25ths. Yeah, no problem. As long as everything makes sense, right? I'm just happy if that's true. Okay, so 4-32. Let me take a look at that one. Oh, this is a great one. I think we were doing this on Piazza, but it might have been a private message, but that's okay. We'll take it up. So 4-32. And then after this one, we're going to do 423. Okay, so just hold on. So 4-32, everyone again, kind of pull it up and take a look. I'm going to read it out, but so it says, you and your friend Hossein play the following game. You each roll a 6-sided dice. If Hossein's dice is larger, you pay him the difference of the shown values, whereas if your dice is larger, Hossein pays you the difference. If your dice show the same amount, then you both keep the money. For example, if 1,5 means you throw a 1 and Hossein throws a 5, then you must pay Hossein $4, right? Because that's the difference. You did a 1, he rolled a 5, so you owe him the difference, which is $4. And vice versa, if you roll a 3 and he rolls a 4, he rolled 1 higher, so you owe him $1. So the question is, what is the expected winnings if you play this game? And then it clarifies, by winnings, we mean the expected value is positive if you win, and negative if you lose, and 0 if you break even, right? So remember, it costs, it doesn't, right. So, okay. So what we're going to do here is we need to figure out what is the maximum amount of money you could win playing this game. Anyone? So you and I both roll die, and whoever has the bigger die wins, and we have to pay each other the difference. In a single, but Jack, in a single roll. Yeah, it's 5. Thank you. It's $5. What's the most you could lose? Right? It's also 5, right? It's also $5. So you could lose $5, or that's the same as winning $5, right? And exactly. And you have, and you can do, Connie, like you say, you can list everything in between. So, and anything in between can happen. So the total way, so we could win, let's put our winnings here. So we can winnings. So we can, the way you should do this is with a random variable, okay? So let X be our winnings. So X 5, 1 is equal to 4, whereas X 1, 2 equals -1, right? Something like this. Hossein was a previous prof. Yeah. Yeah, so this was a final exam question 3 years ago. Yeah. Okay, so does everyone understand how X works? I'm going to feed it the dice rolls, and it's going to tell me whether I win or lose, right? So what we want to do is compute what are all the ways that X could be equal to 5. So you all tell me X equals 5 corresponds to what? Like, what are all the ways that I can win $5? Like what dice rolls have to happen? 6, 1, is there anything else? That's it? I think we all agree that's it, right? That's the only way you can win $5. Okay, what are the X equals 4 rules? 5, 1, and 6, 2. Everyone is agreeing, hopefully. Okay, 3, 6, 3, great. What else? 5, 2, and 4, 1, good. And you just got to keep on going, right? You got to do this for all of them. But what you're probably noticing is you can save yourself a little bit of work if you notice that there's a pattern here. There's only one way of winning $5. There's 2 ways of winning $4. There's 3 ways of winning $3. How many ways, if you had to guess how many ways there are to win $2, how many would you guess? Right, now, is that actually true though? Let's double check it. So 6, 4, right? 5, 3. Yeah, that's true, right? 4, 2, 3, 1. And x equals 1 is, there's going to be 5 ways, right? Let's not even write them all down. 5 ways. And x equals 0 will be 6 ways. Does everyone agree? Right? X equals 0 being you both roll the same die. What are the ways that you can do that? 6, 6, 5, 5, 4, 4, 3, 3, 2, 2, 1, 1. Does everyone agree? Exactly. And the same thing for losing, right? Exactly. There's 36 elements in the sample space. And the probability of these, okay, so let's just kind of beside them do their probabilities. So now what's the probability that x is equal to 5? And as Davin says, this is an important point. The sample space is 36, right? So it's 1 out of 36. What's the probability that x equals 4? 2, right? And again, hopefully we all see the pattern. 3 is, oops, sorry, that should be 2. X equals 1 is 5 out of 36, and the probability that x equals 0 is 6 out of 36. Okay? Yeah, exactly, Dan. Exactly. Now, I think you all agree, this is kind of annoying. We also don't want to repeat this. We have to, but we don't want to do it for x equals -1, -2, -3, and -4, right? Do you all agree? But we still have to do them. But what we can do is we can save ourselves a little bit of time by realizing times 2 the 1 to 5. It depends what you mean by times 2. What I'm going to say is the probability that I lose $5 is the same as the probability of winning 5. Right? Because it's just if you switch the dice around, right? If you switch the dice around, you get the same amount of money lost, but like the same number of dice rolls are possible. Does everyone agree with that? And you can say that, like you should write that in words, right? Like if you're doing this on a test, say, I see that there's the same number of way of losing, or losing just corresponds to the dice all flipping. And so the probabilities are the same. Does everyone understand what I'm saying there? Exactly. And so then, so Jack, you're 100% right, and you're approaching it from exactly the right sort of mentality. But let me just kind of finish this off now. So when we do the expected value, we're going to multiply our winnings by the probability that we get those winnings, right? So we multiply $5, our probability of winning $5, by the probability that we win $5, plus $4 times the probability that we win $4, so on, right? $0 times the probability that we get $0. $1 times the probability that we lose $1, right? Minus 5 times the probability that we lose $5. And as Jack noticed, everything here just cancels each other out, and the expected value is 0. Right? Now, as a mathematician, I would have said immediately the probability was 0. I would have done 0 computations. Why could I? Yeah, this is a very bad casino game, exactly. Why would I, as a mathematician, like how would I argue to say, without doing any computations, the expected value is 0? Like I knew what the answer would be as soon as I read the question. And you tell me, like, how would you argue this, that it was going to be 0 right off the bat? Anyone? Yeah, doubt. Yeah, exactly. So Curdy, maybe like, yeah, it's true. They balance out exactly, which is what I think you're trying to say. Equal chance of, so doubt exactly because there's no entry fee. Well, Jack Poker is the same way though, but like, okay, sure, that's true. You're all, I think, more because of positive wins and negative wins being the same probability, but opposite signs, same. Yeah, exactly. Great. You break even, the difference is 0. It's because it's a fair die. That's a great way of saying it. Exactly. Okay, so I think you've all kind of hit the point on the head. This is what's called mathematically a zero-sum game, right? So if one person gains, okay, yeah, so let me explain. So first of all, if one person gains, they gain exactly what the other person loses. And then more importantly, the game is fair, right? You wouldn't expect anyone, nobody in this game has an unfair advantage. Do we agree? Right? Like both players have completely the same odds of winning as the other, as any other player. It's totally random. This is not skill-based at all. The odds are fair for everyone. And because like, so therefore, how could it be anything other than 0, right? Like whenever I win, right? Like let's say I'm playing against Jack. Whatever I win, Jack loses. And whatever Jack wins, I lose. But the game is fair. We're both equally likely to win and lose. How could it be anything? How could the expected value be anything other than 0? Right? It is a fair zero-sum game. Does that make sense? Does everyone, like that's how I would mathematically justify it right off the bat. For example, though, let's say it wasn't a fair game and my expected winnings were $2 and I'm playing against Jack. What's Jack's expected winnings? Negative, right? Does everyone agree? It's a zero-sum game. There's no money being added from outside and there's no money being taken away. The amount of money in the system can't change. So if I win $2, Jack had to lose $2, right? Does that make sense? This is what a zero-sum game is. There isn't money, like the me and Jack system is completely and totally closed. No one is throwing money on the table for us to play and nobody is taking any money off the table when we play, right? So it's a zero-sum game. If we both paid $1 to play this game, and let's say that we tied, we both lost the $1, that would no longer be zero game. It would actually be possible for us to both lose money, right? Because we both paid to play, and neither of us won. And less likely are where people put more money on the table. That would be rare, but in theory, it could happen. Exactly. We're calculating net winnings. Yeah. Right. This is why, right? So hopefully you guys are starting to see that there's actually economics here, right? So we haven't, like, we're not, the money supply is constant here. For one person to win, another person has to lose. The only kind of problem is that real life doesn't typically be 0. No, but my point isn't like, we're not going to talk about economics. I don't want to talk about economics. But sometimes some students ask me like, well, why are we learning this stuff? How is this stuff useful? I mean, it definitely shows up in in like business, lesser extent management, but there's no doubt. I hope you guys understand. There's no doubt. There's game theory here, right? This is all game theory, and game theory plays a very strong role in economics, right? So this stuff is important. It does show up. So yeah, right. And in fact, an important thing is the stock market. That would be the same for part B. Oh, so for part B though, the game's not fair anymore, right? The game. So I got a direct message saying, would this be the same for part B? So we would do the same sort of calculations, but everyone, if you look at part B, it says, now suppose you manage to acquire a die with the following probability distributions. And the probability distribution, let me write it down so we can see, like, you're a dirty, rotten cheater. I actually had a student write this down once. Like it was part of their answer. They said, because, I think originally it was me and I was cheating in the problem. And they said, because Tyler's a dirty cheater, which I just loved. I thought that was quite funny. Okay. So now you managed to get a die that has this probability. It can't come up 1, 2, or 3, right? It can only come up 4, 5, and 6. And it comes up with 4, 5, and 6 with equal probabilities. this is no longer a fair game, right? I think you all agree. This game is now totally rigged. And so the question is now, right, what is the probability distribution? And when you do this, you actually will now get a different number, right? You actually will have a positive expected value for your winnings. It will be more likely that you will win, right? Okay, so I'm going to leave that computation for you because we're running out of time, and I do want to get to 423 because I did say that I would do it. Oh, it's the damn hurdle question. I think there might be an issue with this question as well. I don't remember. Let's try it. 4-23. So you're jumping hurdles. So the probability of both hurdles is 75%. The probability of the first hurdle is 90%. Having successfully jumped the first hurdle, what's the probability that Lenny successfully jumps the second? So that's the probability of both hurdles given the first hurdle, right? So if we either do this conventionally, it's either BH intersect F over PF, or it's going to be equal to PF given BH times the probability of BH divided by the probability of F. And I think having successfully jumped the first hurdle, what is the probability that Lenny successfully jumps the second hurdle? And I think, again, yeah, the hurdle question, I think, again, I'm missing a piece of information here. Yeah, I need to make a note to myself to fix these questions because what was it? 23 is the one. What was the taxi one? Somebody remind me. $34, thank you. Sorry, everyone. These questions are broken and I just haven't fixed them. You have to make an additional assumption about what will happen. Like it's solvable, but you have to assume something. And depending on what assumptions you make, you actually could get different answers. So. Oh yeah, 424 just isn't finished, right? Thank you. Yeah. Yeah. That's on me, everyone. That's 100% my bad. You can blame me for that. I just hadn't finished those questions. Okay. 5-1. Oh, you did ask that, right? Yeah, let me just do that. Let me pull that up really quick. So for 4, hold on. What did you say for 432? Yeah, Christian, exactly. Because the game is fair. Right, okay. And this is the one that we were talking about on Piazza. Is that the one? Okay, sure. Yeah. So this is 5-1C, and it's to find the limit. I did say I would do this one as well. So I'm going to hang around a little bit just to help do this one. 2 minus root x squared minus 5 divided by x plus 3. See, okay, and it was asked to do this without the conjugate, namely using substitution. So we're going to let u be the square root of x squared minus 5. So u approaches 2 as x approaches -3. Also, u squared is equals x squared. So x is equal to negative square root, right? That's the important thing, u squared plus 5. So, and if I do that substitution, I get the limit as u approaches 2 of 2 minus u divided by 3 minus root u squared plus 5. And this is what I was kind of saying earlier. You don't really have a choice here. You're going to have to do a conjugate. So you can either do the conjugate at the beginning or you can do the conjugate now. 9 minus u squared minus 5. So this gives us the limit as u approaches 2. So this denominator is now what? 4 minus u squared. So that's going to give me 2 plus u in the numerator. 3 plus root u squared plus 5. And then, so it was, so this is, oh no, sorry, this just dies. This is 2 plus u. And now when I plug this in, I'm going to get 3 plus 4 and 5. So that's another 3 divided by 4. So 6/4. So 3 halves. Yeah. So why is it negative? So, you know, this was the same answer that we got. The reason is this right here. Okay. So it says x is approaching -3. Right? So we're saying x has to be close to -3. So x has to be negative. Right? So when I get to this point, and I'm trying to figure out which square root do I take, right? Because you could take either the positive square root or the negative square root. I need to ask myself, is x positive or negative? And because if I take the positive square root, x is going to be positive. If I take the negative square root, it's going to be negative. X is approaching -3, so x has to be the negative square root. This is why, sure, but this is why you were getting the square root of negative numbers, right? Because you were taking the square root of the wrong thing. But like, this goes back to the thing, let's say you have x squared is equal to 4. What are the solutions to this? To a -2, right? But how would you do that? You would say x is either equal to the square root of 4 or x equals the negative square root of 4. So when you take a square root, you have to choose which of the square roots you take, right? And the square root is always positive. Like the square root itself always outputs a positive number. So I need to either say this is equal to 2, this thing here is equal to -2. I have to choose which one I'm going to use. And you usually use some part of the question in order to figure out what you're doing. In our question, we knew that x had to be negative. Right? And so I had to choose the negative square root. Yeah, exactly, because of the negative limit. Yeah, anytime you take that square root, you've got to make a decision as to whether it's the positive or negative square root. It's tempting to just always take positive, but sometimes it doesn't work, right? So you have to just carefully assess whether which of those roots you're doing. Okay, everyone? No problem, no problem. I got to run because I do need to eat. And then I actually have, it's not just your tests today. I actually have 2 others, 157 and 257 I need to set up as well. But thank you, everyone. Good luck today. Good, you know, and or tomorrow, if that's when you choose to write. Hopefully you kill it. I'm looking forward to seeing how you guys do. Yeah, and otherwise have a great weekend. And I will see you next week, everyone. Okay, bye-bye.